We're in section 14.7, which we're breaking into two parts. Part 1 is going to be on homework 4 and going to be on exam 2, and part 2 will be on homework 5 and the third exam. So anyway, the part that we're covering in part 1 of 14.7 is relative extrema and critical points. And so we've done this in Calc 1 in the one independent variable situation, but now we're in multivariate land. So we're talking about having two independent variables. But before we get going on that, let's talk about and review what we did in Calc 1. So we're not actually going over everything we did in Calc 1, just kind of the part that applies to what we're going to do in multivariate land. So here we have this function that's shown in blue, and we can see there's a relative minimum here. It also is an absolute minimum, and so we'll be talking about absolute minimum in part 2 of this section and also in section 14.8. But for now, anything that's locally a low spot, we're going to call that a relative min. And so another thing, I should probably define a little bit better what it means to be a local min in terms of in the neighborhood. So see this point right here at the relative min. What this means is you take an open interval about that point, and that point is less than or equal to, its z-value, I should say, is less than or equal to every other z-value in that neighborhood or on that open interval. So that's like the technical, what it means to be a relative minimum. And so certainly an absolute minimum also satisfies that definition. And so that's sort of an explanation there. Okay, so anyway, a lot of times when you're given a graph, it's pretty easy to tell if there's relative mins and maxes. Maxes, of course, are where you have a locally or in the neighborhood of certain x, you have a high spot. And so I was calling this a z because I'm used to having the dependent variable being a z, but in Calc 1 we were, this was a y. So sorry about that, but okay, so anyway, one of the things we did when we didn't have the graph is we found things called critical values. And so these were candidates for the max and mins, for the local or relative max mins. But it's not that it was a guarantee that there was a max or min there. But it was a good way to just get some candidates, because there is a theorem that says that every single relative max or min is also a critical point. But the theorem doesn't go the other way, so that you can just say, oh, if it's a critical point, then it must be a relative max or min. But we do know that we're going to have all the candidates if we find the critical values, and then we have to use some sort of process to determine, well, is it a relative max or min or neither? So anyway, for this function here, it's x to the fourth minus 4x cubed. And the way you find critical values is you just take the derivative and set them equal to 0, or technically see where they do not exist. So that was kind of one of the cases that happened maybe 25% of the time. But most of the time is when the derivative equaled 0. Then often it was a good idea to try to factor the left-hand side if you could, to find the solutions for this. And so I did that here, and notice that 4 is not contributing any solutions because it's not a variable, but x squared, when it equals 0, and you multiply by all this other stuff, then that's going to give a solution because it's going to be equal to 0 on the right. And so x equals 0 is a solution, and then in this factored form, again, it's multiplication overall. Then you can just take the part x minus 3, solve it for 0. That x is when you also get a solution, because 0 here times, it turns out being 3, all these numbers out front are just going to be 0. And so we get the solutions x equals 0 and 3. So these are critical values. They're candidates for max or mins. And so we did a lot of different things, but again, the analogy or analog for multivariate is going to be the second derivative test. And this actually wasn't a test we used very much in Calc 1, but it's pretty much the thing that we're going to be using in multivariate. So here it is, the second derivative test. Suppose the second derivative is continuous near c, and we got two cases. If the first derivative is equal to 0 and the second derivative is greater than 0, then f has a local minimum there. And so this had to do with concavity. And the other case is when we have the second derivative being less than 0 or negative, then we had a local max. So the idea there was that we would have, it would be concave down at that critical value, then it would have to be a maximum. So anyway, kind of finishing this example up using the second derivative test. Oops. Let's see what we can determine with this function. So I took the second derivative, and then we had the critical values identified already, so we plug them in and we see what the sign is for the second derivative. So there's sort of a weird thing that happens if you get a derivative of 0, then a second derivative of 0, excuse me, then it doesn't have a sign. It's not fitting one of these cases. So if that's the case, we say the test is inconclusive or it's indeterminate, and it doesn't mean that it's not a local max or min there, for example. It just means you can't tell from this test. And so you're going to have a similar thing in multivariate land sometimes. If you check the critical value of x equals 1, you're going to get negative 12. The second derivative evaluator 1, I'm not sure if I said that right. Plugging in, you get negative 12. And so that's a negative. So then we can conclude from the second derivative test that there's a local minimum at x equals 1. So back in Calc 1 with this problem, we would have said, oh, the second derivative is 0. I got to use something like the first derivative test to determine if this is a local max or min. From the graph, we can see what actually is going on is that it's not a critical value. We do have a horizontal tangent line there, but it's not a local max or min. So you'd use some other way of determining that. In multivariate, if the second derivative test doesn't work or it's inconclusive, the test fails, we're just going to say, oh well, okay, I guess we don't know, and then we're going to move on. So anyway, here we go. So here we are in multivariate land, just kind of showing what an absolute, local, and absolute minimum, all those things look like. There's a nice graphic from your book here that I included. And so notice for the absolute maximum, the z attains a high point locally. So here the neighborhood is defined by a disk. So if you can imagine here this absolute maximum, the z is the high point for some radius about it. And so instead of having that open interval about a point like we did in the 2D situation, we have x and y being an independent variable creating a disk, and the neighborhood has now got area, and we're looking at in that neighborhood is z, in fact, the highest place. So same type of thing here. It's just expanding a dimension to 2 independent variables as an input. Similar kind of thing for a local min or relative maximum. And so again, we also have the absolute max and min shown here, but they're also relative mins and maxes as well. So they're both. A lot of times we just label it absolute max if we know it, but we are just talking about relative mins and maxes here. So I included this definition here just to kind of call that out, that this is where not only is it an absolute max, for example, or I mean a relative max in the neighborhood, it's like for the whole city or whatever, the whole region that's being shown here, that it is the highest. So, okay, another thing, we got Fermat's theorem for functions of 2 variables. It says if f has a local maximum or minimum at a, b, so this is the xy that we're looking at, xy coordinate, and the first order partial derivatives of f exist there, then the partial with respect to x there is 0, and the partial with respect to y is 0 there. So this is kind of like actually the critical points, except that instead of just having the derivative overall being equal to 0, because we didn't have to deal with partials there, and we just had one variable, now we're saying the partials, so because we got the 2 independent variables, x and y, that both of their derivatives have to be 0, at the same time. So the and here is very specific in math language. It's saying both these have to happen at the same time, not just one or the other. In that case, you would use an or. So both of those have to be occurring. So we do have critical points in the multivariate situation, and this is how we find them. So just like in Calc 1, or in the one independent variable case, or 2D, the critical points are the candidates. So we find those, and then we use a second derivative test. Well, that's great. Second derivative test is given in, before I talk about it, this format, so you don't need to memorize it. You do need to remember how to find critical values, which hopefully is not too hard, just the partial with respect to x equals 0, partial with respect to y equals 0, and you need to find when both those conditions are being met. And that's how you find the relative maxes and mins. So let's talk about the second derivative test. So here we have our partials again included, and then it has to be differentiable and whatever. Then we have big D. So big D is defined as f double x times f double y, so those are partial twice with respect to x, partial with respect to y twice. At the point, multiply them minus the partial with respect to x, then y, which by Clairaut's theorem we learned we could reverse the order. That was advantageous, and that'd be equivalent. So that's an option. And then we square it. Okay, so you do that calculation, and you can use a determinant for that, by the way, but I'm not bothering to show you that because I just give it to you anyway, so why bother? And so anyway, here are the different cases. Case A, if that D you find is greater than 0, and then the partial with respect to x is positive, then there's a local minimum there. Similarly, if we have the inequality going the other way and we get a negative for the second partial with respect to x, then there's a local max. And then finally, if the D you find is less than 0, then you actually don't need to do any further tests, and you just can conclude in this case it's not a local max or min. So second derivative test is definitely more complicated in this multivariate situation. By the way, if it's not a local max or min, it's called a saddle point. And so this is where you can kind of think of the x and y are not agreeing on whether that point is a local max or min. So it's not a peak in terms of x and y, for example, and there's just some combo of something that's not going on that they're agreeing. So it could be, let's say, a local max in terms of the x's, but a local min in terms of the y's. They would both have the critical value still, because it is a place where you'd have a horizontal tangent plane, but they're not agreeing so that it's actually a local max or min. Any combo of that is called a saddle point. So I have a saddle point shown here, and see the little white point on there is a saddle point, and this is a situation where in terms of x it's a low point, and in terms of y it's a high point, and there is a horizontal tangent plane there, and so it's a critical value, and then but it's not panning out to be a local max or min overall in the 3D situation. So it's called a saddle point. Okay, so, but there could be other combinations of that. It's not, that's the only one. So if you could have an inflection point there, and then a max in the other direction, and that's still called a saddle point. And sometimes they're kind of hard to see. This is an obvious case. Second derivative test is not given in all its glory here, but a shortened version that should help you be able to do this on quizzes and exams. Oh, one thing I forgot to mention is D. What if you get a big D that's 0? Then that's when the test is inconclusive, which means that it could be a max, min, or a saddle point. You just can't tell, and you would just sort of indicate that if that happens. And then again, the way we're doing things here is you're not going to be expected to try to use some other test or some other method to determine what it is. Whereas in Calc 1 it was not as complicated and you were expected to do that. Okay, I'm going to stop the recording here and then I'll move on to example 1 in the next one.